So today we are starting our absolute value unit, but we're also going to be looking at a few more ways that we can describe graphs, to describe their behavior, how we can explain what's happening to other people. So the first thing we're actually going to look at is something called interval notation, and this is going to allow us to explain something called increasing and decreasing intervals on a graph. So let's start out actually going back to something that you talked about in Algebra 1. You did a little bit with inequalities. And so let's look at these examples. We're going to write them first in an inequality and then change that over to write our interval notation. So in number 1, we have an overlap happening. Looks like I have a closed point at -2, a closed point at 3, and I have some shading happening between. So basically, we've got our values. I'm going to use X because it is moving left to right. It's my horizontal axis, which is X-axis when I'm graphing. And so basically, we have X sandwiched in between -2 and 3. So I could write an inequality like that. So X is sandwiched in between -2 and 3. And the reason I use the less than or equal to symbols is because we actually have a filled in circle on our graph. We hit that point exactly. And so here's our new piece. So interval notation is just another way to write this. You're actually still potentially going to use your inequalities when you're writing set notation for like domain and range. But when we're talking about increasing and decreasing intervals, we're always going to use our interval notation. So to show that we hit -2 exactly, we're actually going to use a bracket. And then we go up to 3. And we also hit the 3 exactly. We kind of include that point. And so that's kind of a more condensed way of writing that same inequality. Number 2, you'll notice it's a little different. Number 2 has an open circle at 2. So when I write the inequality for this, I have my value sandwiched between -4 and 2. But because I have that open circle at 2, I don't actually hit it exactly. I don't include that endpoint. I get really, really close to it, but I don't include it. I do hit -4 exactly, so I can use the equal bar on there. And we have our X sandwiched in between. So I could actually read this out as -4 is less than or equal to X, which is less than 2. And we could also read this as X is greater than or equal to -4 and X is less than 2. And so the way we would write this in interval notation, again, when we hit the -4 exactly, we're going to use the bracket. But when we get to where we don't hit the point exactly, we are actually going to use a parenthesis to show that we got really close to that point, but we never hit it exactly. We don't actually include it. So our interval notation, we can summarize it over on the right. If you're going to use brackets, we're going to use those if we include the endpoints. And you might see the vocab used that if the interval is inclusive or including that endpoint. Whereas we're going to use parentheses whenever we're not including that point. So parentheses are used if we do not include, include the endpoint. And actually that should be singular on the top, so I'm going to take out that S. So if we include the endpoint, we use a bracket. If we do not include an endpoint, we use a parenthesis. So then let's look at 3 and 4. So these are, again, we're not going to see this as much with increasing and decreasing intervals, so we won't have to use the interval notation quite so much with these types, but I still want to show you what it looks like. So for number 3, we actually have 2 portions here. Okay, so let's write our inequality. So we've got values, everything including -3 and down towards the end of the graph, which means we're actually going to be going towards -infinity. But we can write this as an inequality as X is less than or equal to -3. But we also have the section going above 0. And again, it doesn't include 0. So we have x is greater than 0. Now, when we have these two sections, we could either be in the left section or the right section. So we usually see or in the middle of that sentence. So again, you're not usually going to have to do this with interval notation this year, but in case it randomly comes up, we would write this in interval notation as, again, everything below -3 means we're going all the way down to -infinity and up to -3. And we're including the -3 because it's a filled-in circle. And you might remember that symbol potentially from geometry. It means the union of our two intervals. That means we've got the stuff on the left or the stuff on the right, all of which we have to consider. And so then we're going 0 and above, but we're not including the 0, so we're going to go parenthesis 0 up to infinity. Okay, then number 4, we're kind of just flipping things around a little bit. So we have our open circle on the left-hand section, our filled-in circle on the right-hand section. Our inequality would look like x is less than -1. Again, no equals to because it's an open circle. Or x is greater than or equal to 3 because it's a filled-in circle. So if we were going to do interval notation on this, we would go from -infinity up to -1, not including it. And we'd have the union with the set starting at 3, which is inclusive. It's including the 3 up to positive infinity. So the reason we have this notation in the first place is we need to start talking about on our graphs whether we have an increasing or a decreasing section. Now, when we're thinking about that, the biggest thing that kind of helps me make sure that I'm keeping my train of thought on these is I imagine myself walking from left to right on the graph. So if it helps, you can even draw a little person on your graph to remind yourself you're going to start by walking to the right. So from the left to the right. So in example 5, my person starts walking on the left-hand side of the graph. Way over on the left, what kind of numbers are we going to have? If graph keeps going on forever and ever, but in the negative direction, eventually it's going to hit -infinity. So my person is starting at -infinity all the way on the left. Excuse me. -infinity. And they're going to walk from left to right. Well, if they start walking on this graph, they're actually going to have to walk downhill. So this first section of the graph is actually a decreasing section. And they're going to keep walking along, and eventually they're going to get to that kind of midway point on our absolute value graph where they get to that bottom point, which you might sometimes hear me call a vertex. That's sitting at -1, -3. But when they get to that point, what's going to happen? Well, they're going to have to start walking uphill. So as they move on the right-hand piece of the graph, again, they're walking from left to right, they're going to be walking uphill. So to express this in interval notation where we're increasing and decreasing, we usually write the increasing one first and the decreasing one second. We are increasing starting at the bottom of the graph. So we're starting at -1, and I'm looking at the x coordinate on here because if we're moving from left to right, what coordinates are those? Yeah. If we're saying where we are moving horizontally, we're always looking at our x coordinates. The y coordinates only come into play in that I'm seeing that I'm walking uphill or downhill. But we always refer to the x coordinates when we're doing interval notation for increasing and decreasing sections of our graph. So we start at the bottom of the graph, the bottom of the V, at -1. And we keep walking uphill and we keep going and going and going forever and ever. So eventually we're going to get to infinity. And we're going to use those same symbols as we did with the intervals. At the bottom of the graph, though, if you're right at that -1 point, right at the vertex at the bottom of the graph, you're not actually walking uphill or downhill. You're just there. You're changing your directions. So when we're doing our interval notation, we do actually use the parenthesis to show that, yeah, right at -1, they haven't started walking up or down yet. They're turning around. parenthesis around the infinity, because again, it's not an exact number, it's just a concept of really, really big. Decreasing, well, the person was decreasing as soon as they started walking on the graph. And again, if we imagine them walking all the way from the left-handmost part of the graph, they started at negative infinity, and they're going to keep walking downhill until they get to that vertex down at the bottom at -1. But again, right at -1, you're not walking uphill or downhill. You're not including that, so it's actually parenthesis. Okay, let's look at the same thing on our example 6. So again, imagine your person walking left to right. If they start on the graph, they're starting way out to the left, technically. So they're starting at negative infinity. And they keep walking and they keep walking and they keep walking, and they're going to have to turn around at the vertex. So they'll be turning around at the point 2, 1. But again, we only care about those x values because we're walking left to right. That's telling us how far left or how far right we've walked. So they start walking uphill. This first section is actually increasing. But as soon as they get to that point 2, 1, they have to turn around and start walking downhill, and they are going to be decreasing until they get to the very end of the graph, except the graph is never going to end. It's just going to keep going forever and ever in that direction. So it keeps going to infinity. So in this graph, we started increasing. Okay. So we started increasing at negative infinity. We keep going until we reach our x value 2, but we don't include it because right at that point, we're actually turning around. And then we decrease or walk downhill. I left that out there. From 2 all the way up to positive infinity. Okay, the last thing we need to talk about today is end behavior. So if you notice on our graphs, so we're dealing with absolute value graphs here, and I'm going to show you a few different graphs as well today. But you'll notice both of the ends are going on the same direction. So the first graph where we had our regular V that we're used to looking at, both of the ends went up. On our second one, both of the ends went down. And there's another graph that does that too, our quadratic, the U shape. The ends do the same thing, but there are graphs that don't do the same thing. So there are some graphs that the ends go in opposite directions. And that can be another thing that we can use to describe what's going on with the graph, what the picture is supposed to look like. So on our end behavior, again, we want to think kind of directionally. As we walk in either direction, what's happening overall to the graph? Is it increasing or decreasing? So we think of this a little differently, so slightly different notation. So we say as x approaches, and that's what we kind of say when we read this arrow. So as x approaches negative infinity, in other words, if you're going to be walking left on your graph, is your y going up or down, and where's it going to? So our first graph here, our green parabola, both of our ends are going up. So it wouldn't matter if I was walking to the left of the graph or if I was walking towards the right of the graph. I'm going to be walking kind of uphill. I'm going to be increasing in both directions. And in fact, if I think in terms of the two values, if I'm plugging in my x values, my function, my f of x, my y values are what's coming out. So what's happening with my y values as I keep going on towards the ends of the graph? Well, they keep going up towards infinity. So for our parabola, as x approaches negative infinity, in other words, as x goes to negative infinity, our graph keeps going up to positive infinity. And as x goes to positive infinity, well, the other end of the graph also going up. That's not happening with the purple graph, though. So notice with the purple graph, we have opposite things happening. So as x is going to negative infinity, if you were to walk towards the left on the graph, you're going to go uphill. So that end behavior, as x is approaches negative infinity, f of x approaches infinity because it goes up. So this is y approaches infinity. But as we walk in the other direction, so as x goes towards positive infinity, our y graph, our y coordinates are going to go down. They keep going further and further into the negative. So as x approaches infinity, f of x approaches negative infinity. Okay. Well, our blue graph isn't all that different from our green graph, except for what? It's still a parabola, but now it's facing down. So that means as I go to x in the negative infinity, I'm going down in the y values to negative infinity. And the same thing happens if I walk to the right. I'm going down in y values to negative infinity. So as x approaches negative infinity, so does f of x in both directions. And then our last one, our orangey yellow graph, what we think of as a cubic. Again, opposite directions happening. So as x approaches negative infinity, we're going down. So y approaches negative infinity. But as we go towards positive infinity on our x's, as we walk towards the right of the graph, our y values are going up. They're going towards positive infinity. And so think back to what we just looked at the absolute value graphs, and they kind of look like parabolas. The ends are always going to go in the same direction. Cubic graphs, they don't. And so the more graphs that we look at, the more we'll be looking at how we can express that end behavior a little differently depending on what that graph is happening. So the last two examples, or last few examples I wanted to look at, are square root graphs. These are a little different with the end behaviors. And again, I just wanted to give you a kind of heads up on this, and we'll see this a little bit more as we go through the year. But don't forget, if we're going to graph our square root function, don't forget it usually starts at the origin and then goes up 1 over 1, kind of almost a reverse check mark, so to speak. But if I throw the +2 on the end, what does that do to my overall graph? Okay. So that actually moves everything up 2 units. So then for this one, if I think in terms of walking left and right, I have a problem. So we usually start with end behavior as x approaches negative infinity. But what happens if you walk towards the left on the graph? Yeah, you don't have anything past that point. So past the point 0, 2, we don't have anything in the negative. So x is actually not going to approach negative infinity. It's going to approach 0 because it can't go any further than 0. And at that point, your y value is equal to 2 because we have a point at 0, 2. But what happens on the right-hand piece of the graph? So if you keep walking to the right, that part of the graph is going to keep going on forever and ever and ever, and it's never going to stop. So as x goes to positive infinity, again, our y's are going to keep going up kind of slowly, but they're still going to be going up. So our y's are also going to approach infinity. So as x approaches infinity, f of x approaches infinity. Let's think about 8. So again, where would we have to graph this? So think about the -2 inside and the -1 outside. If we're inside the function, adding or subtracting, which direction does it go? So -2, your brain thinks, oh, I should move to the left. But inside the function, we always have to take the opposite perspective. So we actually move right 2. And then we have down 1. But every other point has the same relationship. So this one's going to have the same sort of thing happening. We can't walk very far to the left on that graph. We can't walk all the way to infinity. Eventually, we're just going to have to stop at that endpoint. So just like before, x can't approach negative infinity. On this one, it can actually only go to 2. That's the furthest left it can go. And the y value that it gets to when it goes there is -1. But as I walk towards the right, it's not going to stop. So as x approaches positive infinity, f of x, or y, approaches infinity. Okay, last example. Let's put this back together again with our absolute value. So we're going to do all three. We're going to describe intervals of increasing and decreasing, and we're going to describe the end behavior. So there are 2 things happening to this graph. What do you think is going on? you've got the negative out in front of the graph, in front of the grouping. So that's going to flip your graph vertically. And then the -2, just like our previous problem, is going to move it to the right too. So we're going to have an absolute value, so we'll have a V that has its point sitting at 2, 0, but it's flipped upside down. So it's going to look like this. Okay, so again, imagine somebody walking left to right. As I start walking on the graph, I'm going to have to walk uphill. So our increasing interval, again, I'd have to start all the way to the left, so I'm really starting at -infinity. And I get really close to my vertex, not a bad thing to write down the coordinates. And so I get really, really close to 2, but again, right at 2, I'm changing direction, so do we actually include the point? Our decreasing then starts at the 2, but just like we didn't include it on the increasing, we don't include it on the decreasing either. But we keep going and walking further and further to the right, so we keep going towards infinity again in the x direction. So then the last piece is our end behavior. So as x approaches infinity, we need to decide what's happening with f of x. And as x approaches -infinity, again, we have to figure out what happens with f of x. And it doesn't really matter what order you list them in. I tend to default to listing the positive first, but you'll notice I put the negative first. Again, just be very careful that you're reading your directions and reading which one is starting out. Depending on who's written the material, it could be started in either order. So, not a bad idea to write a note for yourself. So as x approaches infinity, are we moving to the left or the right? Well, infinity is positive, so that means we're going to move to the right. So that means as x approaches -infinity, as you're going left. Do your ends ever stop? Hey, no. And do they ever stop going down? So if the ends keep going down forever and ever, that means our f of x in both of these is approaching -infinity. So again, as always, let me know if you have any questions. Pop back into Zoom if you need to check in or run a couple extra examples. See you later.